Hi everybody, thank you for being here. So, what's going on? This is a physics course. You may or may not believe that you know physics. You may have taken high school or college physics a few years ago or a few decades ago, but even those who have never learned about physics in any formal capacity still live their lives with a fully operational belief system about the physical world and how objects interact. These mental structures start forming from infancy, and throughout our entire lives, our brain is working consciously or subconsciously to identify patterns and make sense of what we see. So even if you can't recite Newton's laws of motion, I know you've got some working knowledge of the related concepts somewhere. What I'd like you to do in this course is take that knowledge, bring it forth, test it, play around with it, see where we get. Maybe you'll revise some ideas that you've had for a long time. Maybe your ideas will be validated. You might identify gaps in your understanding. Hopefully, you'll learn some interesting stuff, think about an everyday situation in a new way, or even get a little existential about our place in the universe. Now, this obviously isn't a typical physics course. When I teach, I really enjoy interacting, talking with students, getting to know where their head's at. And students really benefit from that sort of live discussion. And I'm available anytime if you have any questions or ideas or want to chat about anything. But when you watch these videos, you're going to hear me ask a lot of questions. This is by design. I'm really asking you. I'm not going to ask you to take notes or do homework or do calculations or anything really formal like that. I want this to be a chill experience, and I also want it to be useful. In order to help you be more engaged, more of an active participant, I want you to really think with me. Even pause the video if you'd like a moment to chew something over. By thinking with me, coming along on thought experiments, visualizing different scenarios, you're going to take more control over your learning, become more aware of your ideas, and have a greater chance at really developing them. So, let's do it. All right, in this course, we're going to be talking a lot about motion. So to start, let's lay down some basic ideas and terminology so that we're on the same page when we talk about the way something moves. Very first off, we've got position. This just means the place where something is. Easy, done. We've got time, time. We might talk about an instant in time, like a snapshot of what is happening at that very moment. And we might talk about something that happens over a period of time. For example, the position of an object might change over time. When that happens, the object is moving, and it must be moving at some speed. You know speed, right? I think we've all got a pretty intuitive sense of what we mean when we talk about the speed of an object. It's the rate at which its position is changing over time. Really, in this course, we're not going to be all that concerned with numbers. When we talk about speed, we're mostly going to be talking about relative speeds. Is the object moving really fast? Is it creeping along slowly? Is it stopped? Is it moving at a constant speed? Then we've got velocity. Now we're getting into the more physicsy lingo. But just like you might use speed to talk about how fast an object is moving, we use velocity to talk about how fast an object is moving and the direction that it's going. So with identifying velocity, we'll mostly want to just get really good at identifying explicitly the direction that the object is moving at a given instant in time. Knowing about the direction of an object's motion is going to become a lot more applicable later in this course. For now, let's just fire through some quick examples to get practice thinking about this. Say an apple is falling from a tree. While it's falling, its velocity points down. Say I pick up that apple and throw it straight up. While it's on the rise, its velocity points up. At some point, its velocity is going to reverse and point straight down again when it falls back down to earth. Straight line motion is pretty straightforward. Let's look at something that's moving along a curved path. Now, in this course, we're going to be doing a lot of visualizing, and I've got this to help us out. Physics involves a lot of diagrams, and little diagrams are going to be our friend here. Now, I'm not going to ask you to draw along at home. I want the skills that you gain in this course to be readily applicable wherever you are, without a pencil and paper or calculator or whatever. But for the sake of clarity, I'm going to use the iPad just to illustrate what I'm thinking every once in a while. So, say I'm throwing an apple, and this is the path it's going to take. Because the path isn't a straight line, the direction of the path changes. We know that the direction of the apple's motion is going to change. When I first throw the apple like this, its velocity is pointing up and to the right. A moment later, when the apple is at the top of its arced path, what direction do you think its velocity is pointing? Well, the apple is always traveling to the right. On its first half of its journey, it's traveling up and to the right. On the second half of its journey, it's traveling down and to the right. So directly in between those two halves, when it's at the top of its path here, it's simply traveling to the right. It's in the process of changing from upward to downward motion, all while traveling to the right. Let's do another one. Say a person is walking in a circle. This is a top-down view. Say they're just going counterclockwise, round and round. When they're here, at this point, their velocity points this way, a direction that we can call up. How about when they're here? Which direction do you think their velocity is pointing now? It's to the left. And here, it's down. What about here? It's to the right. You might notice a pattern here. Their velocity is always pointing tangent to the circle, or a line that's just skimming the outside of the circle. Another way to think about it is this. If I mark out the very center of the circular path and connect a line between the center of the path and the person, their velocity is always pointing at a right angle, perpendicular at 90 degrees to that line. Their direction is always changing, but from the point of view of the person, they're always facing forward. Their body is always pointing in the direction of their next step. We'll learn more about things moving in circular or curved paths later in the course. But for now, it's good to just note that for any object following a curved path, their velocity at any instant in time is a tangent to that curved path. And before we move on, I'll pose a sort of a challenge question. Say I throw an object straight up. It's going to travel up, it's going to reach some maximum height, and then fall back down. But when the object is at that maximum height, at its peak position, what is its velocity? Can we give it a direction? Well, we know that when that object is traveling upwards, its speed is decreasing. It's going to go slower and slower until it reaches that maximum height. So when it's at that height, what is its speed? Well, what's the slowest speed anything can have? 0, right? At that very moment, between when the object is moving up and moving down, at that exact moment, the object is actually stationary. At that moment, its speed is 0. And then, of course, because of gravity, it starts to speed up, going faster and faster as it falls down. More on gravity later in the course. But we've seen that gravity causes an object's speed and its direction of motion to change. And we have a word for when an object's velocity changes: acceleration. Acceleration is defined as a change in velocity over time. So an object might change its speed, it might change its direction, or both. So long as an object's motion is changing in some way, we say that it's accelerating. When I throw an object straight up and it's slowing down, that's accelerating. And when it falls back down to earth and speeds up, that's accelerating too. Now, because acceleration is a change in velocity over time, an object's acceleration can be great or it can be small, or somewhere in between. It depends on how quickly the velocity is changing, or the rate of that change. We talk about this a lot when we talk about cars, like 0 to 60 in 3.5. Rihanna is specifying a change in velocity, namely a change in speed, over a given amount of time. So compare riding in that sports car with Rihanna to driving a car going 0 to 60 in, say, 30 seconds. It's going to be two very different experiences. Both have the same change in velocity, but it's done over a different amount of time. Again, we won't be doing computation in this course, but it's good to think about these qualitative relationships, like same change in velocity over less amount of time means greater acceleration. And just like acceleration has a magnitude or size, acceleration has a direction. If an object is accelerating, it must be accelerating in some direction. We can think of the simplest case for this. Say we have an object that starts at rest. Then it starts moving to the right. We know that it's accelerated to the right. Or if the object starts at rest and then starts moving to the left, we know that it's accelerated to the left. In this course, we'll be thinking a lot about the directions associated with things like velocity and acceleration. Think about an object that's falling down. Its velocity points down because that's the direction it's moving, and it's moving faster and faster in the downward direction. Its acceleration and velocity both point down. When an object's acceleration and velocity point in the same direction, that means that the object is speeding up in a straight line, and that's what we observe, right? But what about an object that's thrown straight upwards? Its velocity points upwards because it's moving in that direction. But is it accelerating upwards? Is it speeding up? No, it's slowing down. Its acceleration is actually pointing in the opposite direction. So here, velocity and acceleration point in opposite directions, and that means that the object is slowing down in a straight line. Velocity and acceleration can even point perpendicular to one another, or at some other angle, and when that's the case, we see a change in direction, not just a change in motion in a straight line. Moving on, here's a question. Imagine we have two figure skaters, and one is much larger than the other. They both stand facing each other with their hands out, and they press against each other. They push off against each other. Which skater, if any, exerts the larger force on the other? Do they exert any force at all? Might they exert the same amount of force? I'll give you some time to think it over. But what is force? In simple terms, a force is a push or a pull. You're familiar with forces in everyday life in that they act to change the motions of objects. You push on something, you pull on something. Gravity pulls something down. You tug on a rope. Magnets attract or repel each other. There's a common theme here. Every force, every single one ever, is a result of an interaction between two objects. Any push or pull that you can identify happens because of an interaction between two objects. Granted, an object can interact with more than one other object at the same time, but for each pair of interacting objects, there's a pair of forces that result from that interaction. Now, there are different types of forces, and in this course we won't really get into specifics, but I gave you some examples a moment ago. And any type of force, any type of physical interaction can be categorized as one of two things, a contact force or a non-contact force. A contact force is pretty much what it sounds like, a force that results from two objects that are in contact with each other, literally touching each other. Most of the forces that we encounter on a daily basis are contact forces. When you grab something, that's contact. When you pull on a rope and provide tension, you need to have that contact. Friction is a force that results between two surfaces in contact. So what are non-contact forces? These are forces that act at a distance, where two objects interact, but they're not directly touching each other. Think gravity. Gravitational force keeps the moon orbiting Earth, keeps Earth orbiting the sun, holds the galaxy together. Even though those stars and planets aren't touching each other, they're still interacting through the force of gravity. Those are really the only non-contact forces. And in this course, we're not even going to get into electromagnetic stuff. So gravity is the only non-contact force that we're going to be concerned with here, and we'll get into that later. So either way, a force is essentially an interaction between two objects. It's not some internal property of an object. When I throw this ball, I'm applying a force on it, but I would never say that I'm putting force in it. Force isn't something that can be stored inside an object or passed back and forth. Whenever there's an interaction between two objects, there are forces on either object. A given force is simply a push or pull on an object due to its interaction with another object. When those objects stop interacting, the force ceases to exist. Forces only exist as a result of an interaction. Now, I'm talking a lot about objects in general, not just people or living things. Some intro physics students have an idea of an active force, where force can only be applied by a living object. By this logic, an inanimate object could never exert a force because it can't think about how it's going to interact with another object. But by interaction, I don't necessarily mean something intentional or personal or alive. Sure, I can interact with this ball, but this ball can also interact with this can. For a moment, they're in contact, no? So they're interacting and exerting contact forces on each other. Now, similar to what we've learned about velocity and acceleration, any force must be described with both a magnitude or a strength and a direction. A force can be weak or strong. It can point up, down, left, right, forward, back, or any direction in between. So in order to fully describe a force, we have to identify both its strength and direction. What's going to help with this a lot is representing forces in diagrams using arrows, where the length of the arrow represents the magnitude or strength of the force, and the direction simply represents the direction that the force acts. Since we're not really concerned with numbers in this course, we'll mostly be describing relative magnitudes of forces by drawing arrows with different lengths. So say we have two objects and each one has a force acting on it. This object has a great force acting to the right, and this object has a relatively weak force acting down. So we would represent those forces like this. The greater force is represented by the longer arrow, and each force points in the direction that it acts. Hammering this point into the ground, force is literally always the result of an interaction between two objects. Like I said, an object can interact with more than one other object at a time, but we'll get into that later in the course. For now, let's think about an interaction between a pair of objects. That interaction involves a pair of forces. Maybe this is familiar. It's Newton's third law of motion. I'm sure you've heard it before. For every action, there is an equal and opposite reaction. And yeah, that's like all good and stuff, but we're gonna abandon that terminology entirely. There's a much better way to state Newton's third law, in my opinion. So what's my damage with action and reaction? Well, using those words kind of implies some sequential order. Like the action force acts first, and then the reaction happens sometime later as a reaction. But this is false and misleading. In reality, the forces happen simultaneously. Both forces originate in the same event, and both forces are equally as valid. We shouldn't place more importance on one force than the other by just saying that this one's the action and oh, that other one happens as a reaction sometime later. So let's reframe this. Here's a better way to state Newton's third law that's more helpful when you're actually trying to analyze the forces in an interaction. If object A exerts a force on object B exerts a force on object A that is equal in strength and opposite in direction. So there are two forces, the force of A on B and the force of B on A. Those two forces make up what we call a Newton's third law force pair, or just force pair. It's a pair of forces acting between a pair of interacting objects. And those forces are equal in magnitude or have the same strength and opposite in direction. Now, this might not be immediately obvious. If I lean on a wall, is the wall exerting a force on me? What does that look like? Well, I could ask you, why isn't the wall just letting me pass on through? The fact that the wall is holding me up, it's not letting me pass right through its surface, is evidence that the wall is exerting a force on me. And I can feel it too. I can feel the wall pressing on my hand. For my job, I actually just got finished designing a physical sciences unit in which we use baseball to teach the kids about concepts like force. So I've got some great illustrations saved for this. The interaction I want to show you is between the ball and the bat. Because of Newton's third law, we know that these objects must be exerting force on each other. And we can see really cool evidence of this. Here's a slow motion video. The force of the bat acts on the ball to deform it. The ball is sort of elastic, so it gets misshapen. There's a lot of force acting on the ball, acting to accelerate it really quickly in the opposite direction. And following Newton's third law, we know that the ball must also exert a force on a bat. We can see this when the bat itself gets misshapen. The bat vibrates, so much so that it even breaks sometimes. So it's not just one object acting on the other, it's an interaction. Those types of motion make the interaction a lot more obvious to the eye. But what about something as mundane and motionless as, say, a book resting on a table? Newton's third law tells us that these objects must be exerting force on each other. But how is this? To be fair, it's not immediately obvious how a table exerts force on a book. But imagine for a moment that you're the table. Think about like if you've played with kids on all fours and you're in tabletop position and the kids are climbing on you. You certainly feel the downward force of their weight on your back. But you know that you also have to provide force in order to hold them up. Think about if more and more weight gets piled on your back. The more stuff is on you, the more you feel it weighing you down. And the more you also have to engage your body in order to hold it up. You can certainly feel the difference between, say, a toddler on your back versus a whole group of rowdy kids. The more weight is pressing down on you, the more you have to press back to support the weight. And at a certain point, if there's too much weight on you, you're gonna give out, you're gonna collapse, just like a table might if you put way too much weight on it. Remember, A acts on B and B acts on A. In fancy terms, we might call A and B the agents of force. If you ever find yourself needing to identify the force pair in an interaction between two objects, it's as simple as switching the objects, or agents, around. Say we want to find the force pair for the case of my water glass sitting on my desk. The two objects, or agents, are the glass and the desk. So we say that the glass exerts a force on the desk, and the desk exerts a force on the glass. And we know that these two forces are equal in strength and opposite in direction. But we have to be careful with this, because sometimes it's easy to get a little trigger happy, and anytime we see two forces that happen to be equal in strength and opposite in direction, we might think that they must constitute a force pair. Let's return to the example of the book on the table. We know that the book has some weight here on Earth, so there's a downward force of Earth's gravity acting on the book. And the book is also being supported by the upward force of the table. These forces acting on the book are balanced, meaning they're equal in strength and opposite in direction, so they essentially cancel the effects of one another out. But is this a Newton's third law force pair? They are equal and opposite. But no, they're not actually a proper force pair. To start, the forces in a force pair always must be of the same type. They arise in the same interaction, so a gravitational force must be paired with another gravitational force. Or for example, a force of tension, like the upward force of my hand on this shoelace, must be paired with another force of tension, like the downward force of the shoelace on my hand. Let's return to the example of the book on the table. The two forces we identified were the downward gravitational force of Earth acting on the book, and the upward force of the table acting on the book. That's a non-contact force and a contact force, so they can't make up a force pair. Can you spot anything else that's wrong with this false force pair? How many objects are we talking about in these interactions? Well, there's the Earth, the book, and the table. That's 3 objects. Remember, Newton's third law force pairs concern an interaction between exactly 2 objects. But an object can interact with more than one other object at the same time. And that is what's happening here with these forces on the book that we've been talking about. This is 2 interactions. The book is interacting with 2 other objects. So we can actually identify 2 Newton's third law force pairs. Can you identify them? Well, if you're struggling, just start by naming the 2 objects in the interaction. We're talking about the book and the table. So we know there's a force of the book acting on the table, and there's the force of the table acting on the book. In which directions do they point? Well, the table acts to hold the book up, so that force points upward. Then we know that the force of the book on the table points downwards. And for the other force pair, we have Earth's gravity. So Earth is interacting with the book. So there's a force pair of the downward gravitational force of Earth acting on the book and an upward gravitational force of the book acting on Earth. How is this? Think it over, and we'll circle back to it later. For now, we can circle back to the question about the figure skaters. There's 2 skaters. Say figure skater A is a lot bigger than figure skater B. The skaters push off of each other, so we know that A is exerting a force on B and B is exerting a force on A. But which skater exerts the larger force? Well, we've learned that they must exert the same force on each other. There's a common misconception that in an interaction, the heavier or larger or faster or more active object applies more force and wins out over the other one. But we've seen that this must not be the case. So then why do we see different reactions for the same force? Like for the skaters, we expect to see the smaller skater go flying off and the larger skater to move much slower. And this is indeed what happens. In a collision between a semi-truck and a car, why is the semi-truck pretty much fine and the small car gets messed up? So how can the same strength of force produce very different results on different objects? I'll leave you with that to chew over as well, and we'll discover the answer together in a later session. Okay, that's all for now. Let's have a brief review of what we've gone over together. We saw that when the position of an object changes over time, it must be moving with some speed in some direction, and we use velocity to describe both of those things at once. We also saw that when an object's velocity changes over time, it must be accelerating in some direction. An object's velocity and acceleration can point in the same direction, making that object speed up, or they can point in opposite directions, making that object slow down. Or if they point at some other angle relative to each other, we know that the direction of the object must change. We'll get into this more in a later session. In this lesson, we also learned that forces arise from an interaction between exactly 2 objects. Any pair of interacting objects must have a pair of forces acting between them. These forces must be of the same type and be equal in strength and opposite in direction. One might say that you and I are interacting right now through the force of knowledge. And that, my friends, is a force that can act at a distance. I appreciate you. Thank you for being here, and I'm looking forward to seeing you back here next time.